So we're going to talk about Section 7.1 today. Section 7.1 is an introduction to hypothesis testing. So one big part of statistics is claims. Claims that are made by individuals, claims that are made by companies, claims that are made by manufacturers. So to use statistics to its utmost potential, we must be able to test claims that are made. Are they likely to be true or more likely to be false? And the process of evaluating the likelihood of claims is what we call hypothesis testing. Why do we need to do this? Well, we constantly hear claims through advertising and other settings. Go watch a television show. And while you're watching that television show, pay attention to the commercials. Don't just fast forward. And you're going to see a ton of commercials that have some sort of statistical information in it. This box of cereal has 30% more raisins than the leading brand. That's a statistical statement. The 2011 Ford Fusion gets an average of 32 miles per gallon on the highway. That's a statistical statement. This new light bulb lasts for 1,000 hours. That's a statistical statement. So when a manufacturer or an advertiser makes a claim like this, are we supposed to automatically believe it? Or is there some way that we can try to verify their claim? So being able to test claims like this is central to statistical investigation. All right, so thinking back to those three claims that we just had on the screen, let's talk about the light bulb claim. What if we wanted to test that light bulb claim above? How might we do it? First, we would want to take a random sample of the light bulbs in question. And we would want that sample to be greater than or equal to 30 if possible. Now, think about this. This is actually a very complicated matter, being able to take a random sample of light bulbs. How would we do it? You can't just go to the store and buy 40 light bulbs. That's not a random sample. That's a biased sample. If you're getting all of your light bulbs from the same store, then you're running a risk. And why are you running a risk? Well, if the shipment of light bulbs was damaged to that store, they may have a shorter life than other light bulbs of that brand. Or if other light bulbs are constantly being damaged, but this shipment is on a nice, well-paved road, and they don't have any problems with the shipments to this store, but other stores do, then you might get a sample that has an uncharacteristically high lifespan. So you would want to be able to buy one light bulb from multiple stores, not just in one city. You would want to do it all across the country. That can be a daunting task. So this, even though we state it very simply, is not necessarily a simple thing to do. But once we figured out how we're going to do that, then we would want to test the life of the light bulbs and find the mean and the standard deviation for this sample. This also is not as straightforward as it sounds. How are we testing these light bulbs? So we stick them in a lamp, right? And we're going to run that lamp and see how long the light bulb lasts. But would it be fair to run the light bulbs in different lamps? Because if the wiring in a different lamp is a little bit different and it carries more of a charge than a different lamp, or if there's a short circuit or something like that, then one lamp might give you very different results than another lamp. However, if we're testing these light bulbs for 1,000 hours, there's 24 hours in a day, you're talking about more than 40 days to accomplish one light bulb. And if you've got a sample of 40, now you're moving into more than 1,600 days. You're talking about a 5-year deal if you're using the same lamp. So you have to start making concessions and saying, okay, well, we'll use these 40 lamps that are all the same manufacturer, and hopefully that will reduce some of those problems. You do really have to be careful about testing the product in a different mechanism, because that different mechanism may cause differences in the results. And those are the kinds of things that you would have to note in your study at the end. So then, once we've done this, how do we make our decision? Well, if the mean is too far from the claim, then we reject the claim. If it's relatively close to the claim, we don't reject the claim. That language is not very specific. we say if it's too far from the claim. Well, what constitutes too far? How far is too far? Or if it's relatively close, well, how close is close enough? That's the real question. How do we know if the sample value is close enough for us to consider this a nice normal sample and not doubt the claim? And all of this goes back to the central limit theorem. So let's look at an example. We're going to do that light bulb problem. A light bulb manufacturer claims its new bulb lasts for 1,000 hours. For these bulbs, the value of sigma is 32 hours. You want to test this claim. You take a random sample of 64 light bulbs and find the following. The mean of the sample was 987 hours. So should we believe the claim? Okay, so looks like we've already got our testing done. Since we're talking about the probability that the average for a group falls in the particular range, this is an application of the central limit theorem. If we were just talking about one light bulb and where its lifespan falls, then that wouldn't be central limit theorem. But once we start talking about groups of individuals, that's when the central limit theorem comes into play. So whenever we do a hypothesis test, we always assume that the claim that they're making is true. And then we determine if the calculations we make us change our mind. Right? So we're giving them the benefit of the doubt, assuming that their values are true. Then if that leads us to a contradiction, we'll cease to believe their claim. So the question we're really asking is, what is the probability that a random sample would have a mean of 987 or less? Okay, so we're going to look at our central limit theorem values. That means we need to find mu of x bar, sigma of x bar. So mu of x bar, which is mu, is 1,000. Sigma of x bar, which is sigma divided by the square root of n, is 32 divided by the square root of 64, which is 4. So we're looking for the probability that x bar is less than 987. So we calculate our z-score, and that z-score, z equals x bar minus mu of x bar over sigma of x bar, is going to be 987 minus 1,000 over 4, which is negative 13 over 4, which is negative 3.25. So let's go ahead and find a table value. If you look this up on the standard normal distribution table, a z-score of negative 3.25 has a table value of 0.0006. We wanted to know the probability that the average was less than or equal to 987. And so with a less than probability, the table value is our probability. So the probability that a random sample would have a mean of 987 or less is 0.0006, which is 6/100ths of 1%. Now that's not a very likely thing to occur, right? It's 99.94% that wouldn't happen. The chances are that the manufacturer's claim was false, because that doesn't sound like it's close enough for us. So that's kind of how hypothesis testing works, but that's a very simple example, and there's a lot of formal processes that we have to learn to be able to really get it to where it's a nice, tight process that we can use. Okay, so we need some definitions if we're going to figure out this whole hypothesis testing thing. First is the definition of a statistical hypothesis. A statistical hypothesis is a statement about a population parameter. And it's not just one statement. These always come in pairs. So the two different hypotheses that we have are the null hypothesis and the alternative hypothesis. So what the null hypothesis is it's a statistical hypothesis that contains some statement of equality. It doesn't just have to be equals. It could be greater than or equal to, less than or equal to. As long as there's an equal to part in that statement, then it qualifies as the null hypothesis. The other hypothesis is called the alternative hypothesis, and we use HA as a symbol for that. And so in the alternative hypothesis, There is no equality. It's a statistical hypothesis that contains a statement of strict inequality. The way that these two hypotheses work is that if one of them is true, the other one is false. So when H naught is true, then HA is false, and vice versa. When HA is true, H naught is false. They cannot both be true at the same time. They're mutually exclusive. So let's look at an example. We want to state the null and alternative hypotheses for the following three situations. Situation A. The manufacturer of a light bulb states the average life of its newest bulb is more than 1,000 hours. Statement B. A medical study states that 59% of study subjects showed improvement while taking a new medication. And statement C. A cell phone company claims the average number of dropped calls on its network is no more than 1,500 per day. We're just setting up the hypotheses here. We're not trying to solve a problem. We're not trying to determine if a claim is true or not. We just want to know, can we set up the hypotheses? Because if you can't set up the hypotheses, then you can never perform a hypothesis test. You can never verify a claim or doubt a claim if you can't ever set up the hypotheses in the first place. Okay, so what we're going to do is we're going to use each one of these statements to form a hypothesis. And then once we've done that, we'll describe that as either the null hypothesis or the alternative hypothesis. And then we'll come up with the other hypothesis. So in these statements don't contain both hypotheses. They'll contain one hypothesis, and then using the fact that they're mutually exclusive, we'll come up with what the other hypothesis would be. So for the first claim, that the manufacturer of a light bulb states the average life of its newest bulb is more than 1,000 hours, we want to think about what's being said here. We can strip away a lot of what's there, and it says the average is more than 1,000. So if the average is more than 1,000, how would we write that mathematically? Well, that would be mu, the average, right? We're talking about the population average here. Mu is greater than 1,000. So that would be one of the two hypotheses. The question is, which one? So to determine which hypothesis we have, we're really asking, do we see an equal sign or not? If we see an equal sign, then it's a null hypothesis. If there's no equality part of it here, then it's the alternative hypothesis. So this is not greater than or equal to, it's just greater than. It's strict inequality. And that makes this the alternative hypothesis. So that means we need to come up with the null hypothesis. So what's the opposite of being greater than 1,000? And a lot of times people say less than 1,000, but that's not true. You could also be equal to 1,000. So it's not just being less than 1,000, it's being less than or equal to 1,000. Because there's three things. There's greater than 1,000, less than 1,000, or equal to 1,000. Since the alternative hypothesis contained the greater than 1,000 part, the null hypothesis has to contain the other two. It has to contain the less than, and it has to contain the equal to. So its complement is H naught, which is going to be mu less than or equal to 1,000. So these are my two statistical hypotheses. That H naught is mu less than or equal to 1,000, and HA is mu greater than 1,000. Let's look at part B. That's the one about the medical study. A medical study states that 59% of subjects showed improvement while taking a new medication. So again, we're going to strip away the parts. That 59% showed improvement. This isn't about an average. This claim is not about mu. We're talking about some proportion of the population, right? If you remember right, in section 6.3, we talked about finding margins of error and confidence intervals for population proportions. This is about a population proportion. So instead of using mu as our variable, we're going to use p. And that is an equal sign. It's not that more than or that less than, but it said that 59%. That's an equal sign. So we're looking at p equals 0.59. So we need to know, is that the null hypothesis or the alternative hypothesis? And so because there's equality in this, it's the null hypothesis. It's H naught. That's how we pronounce the H with the little zero, H naught. So what's the opposite of being equal to a number? It's not equal to that number. So P not equal to 0.59. And that would be our HA. So my two hypotheses, the null hypothesis is P equals 0.59. The alternative hypothesis, P not equal to 0.59. How about part C? That's the cell phone company problem. A cell phone company claims that the average number of dropped calls on its network is no more than 1,500 per day. So again, we need to strip out what's happening here. We see the word average. So that tells me that this is a claim about mu. Is no more than 1,500. My claim is that the average is no more than 1,500. That means that it has to be less than 1,500 or equal to 1,500. So mu less than or equal to 1,500. Because no more than means it's not greater than that. It's not greater than 1,500. So that must mean it's either less than 1,500 or equal to 1,500. So would that be the null hypothesis or the alternative hypothesis? And again, that's a question about the presence of an equality. Is there an equality here or not? Well, this says less than or equal to. So there is equality, which makes this the null hypothesis. If that's the null hypothesis, being less than or equal to 1,500, the alternative hypothesis must be the flip side of that, which would be greater than 1,500. So mu greater than 1,500. So your two hypotheses are H naught is mu less than or equal to 1,500, and HA mu greater than 1,500. Okay, so it's time for a practice problem. And you're going to do the same thing that we just did here in the example. You're going to state the null and alternative hypotheses for the following. At a department store, the average number of merchandise returns per day is 13. A medical study states that the proportion of the population that suffers from lupus is less than 4%, and the average number of babies born in Fresno County each day is at least 3. So give those a shot, try to figure out the null and alternative hypotheses, pause the video, and when you're ready to find out what the answers are, press play. So, we're going to use each one of these statements to form a hypothesis, and then we'll determine whether it's the null or alternative hypothesis, and then of course the complement to that will be the other hypothesis. So for the first one, at a department store the average number of returns per day is 13. Let's pick up on our key words here. We see average, and we see the word is with the 13. Is not a greater than, it's not a less than, it's an equal to. So this is mu equals 13. Would that be the null hypothesis or the alternative hypothesis? Well, because there's an equality in it, that's the null hypothesis. That's H naught. So now we need to find the HA. Well, what's the opposite of being equal to something? It's being not equal. So the other one, HA, is going to be mu not equals 13. For part B, a medical study states that the proportion of the population that suffers from lupus is less than 4%. So we've got proportion is less than 4%. So we're not talking about mu here, we're talking about a population proportion P. So we've got P less than 0.04. We always convert our percentages into decimal form. There's no equality here, so this is the alternative hypothesis. So the opposite of being less than would be greater than or equal to. That's going to be our H naught, P greater than or equal to 0.04. So those are our hypotheses for part B. In part C, the average number of babies born in Fresno County each day is at least 3. So our average is at least 3. At least means it's at that level or more, right? It's either 3 or more. So 3 or more would be greater than or equal to 3. Mu greater than or equal to 3. Because there's equality, then that's the null hypothesis H naught. The opposite of being greater than or equal to is being less than. So HA would be mu less than 3. And those are your two statistical hypotheses. So we have a little note here. H naught will always contain one of these symbols, either an equal sign, a less than or equal to sign, or a greater than or equal to sign. That's one way you'll always know where H naught is by looking for these symbols when you create your hypotheses. If it has any one of these 3 symbols, then it's going to be the null hypothesis H naught. When we're performing these hypothesis tests, we get a claim from a manufacturer or an ad agency, and we go to test that claim, and we make our decision. The thing about making that decision is there's always a possibility we mess it up. So there's always a chance that we've made an error. This is due to the use of a sample that may not accurately represent the population. You might accidentally reject the right hypothesis. So maybe the claim is absolutely true, and you say, no, I don't believe it because the sample that I got was an unusual sample. And so based on the unusual sample that I got, it didn't seem like it was possible, and so I doubted the claim. The other thing we might do is we might not reject the wrong hypothesis. So we may take a sample, and that sample may make it seem like the hypothesis is true, but what if our sample is very strange, and if we took 1,000 other samples, every one of those 1,000 other samples would show that that hypothesis was false? So we might not reject the wrong hypothesis, because when we say that the chances that a sample would be this is very small, that means there's still a possibility, and we might actually get one of those samples that falls in that very unusual range, being outside of 3 standard deviations. Remember, outside of 2 standard deviations is unusual. Outside of 3 standard deviations is very unusual. So if we get one of those samples that's very unusual, we might make the wrong decision. So each one of these error types has a different name. So we're going to talk about the types of errors in a hypothesis test. They're just numbered. We have a type 1 error, and in a type 1 error, that's when you reject H naught when it's actually true. And then we have a type 2 error, and that's when we don't reject H naught when it was false. So we might reject it when it's true or fail to reject it when it's false, and those are type 1 and type 2 errors. Each one of these has its own name, and it's a name that you might be more familiar with. A type 1 error is also called a false negative. So when you're rejecting a claim and it shouldn't be rejected, that's a false negative. When you are failing to reject a claim when it should be rejected, that's a false positive. Where do you hear the terms false positive and false negative? And a good example of that is in medical tests. So it could be a pregnancy test. Sometimes there's false negatives, sometimes there's false positives. Each one of those has its problems. Drug testing. You'll hear, I tested positive for opioids, but I haven't had any opioids. And maybe you had a poppy seed muffin, and sometimes if you consume a lot of poppy seed muffins, those poppy seed muffins will make it look like you've been taking opioids. So You might get a false positive for having taken an opioid. Each one of those errors comes with its own types of problems. Sometimes a type 1 error is very bad, sometimes a type 2 error is very bad. So we're going to do an example to kind of show that situation. Example. A toy manufacturer claims that the proportion of its toys contaminated with lead-based paint is less than 1/100th of 1%. Describe a type 1 error and a type 2 error, and which one is worse. Okay, so we don't really want any toys with lead in them. That causes all kinds of problems. So let's think about what that said again. It said that the proportion of its toys contaminated with lead-based paint is less than 0.01%. So proportion is P less than 0.01. That is the alternative hypothesis. That's actually the claim that's made within the statement from the manufacturer. So the opposite of being less than 0.0001 is being greater than or equal to 0.0001. And that's my null hypothesis. Notice, this is in decimal form. The original problem was given to us in percentage form, but we always convert our percentages to decimals by moving the decimal place 2 places to the left. So now that we've got our hypotheses, we can think about what each one of these error types would be. So let's start with a type 1 error. A type 1 error happens when we reject H0 when it's a true statement. So in this error, rejecting H0 when it's true would mean that we'd be accepting HA when it's false. So what would be the result? Well, this error would cause you to believe that the proportion of contaminated toys was less than 1/100th of a percent when it was actually more. Okay, so you would believe that it was less than 1/100th of a percent, but actually it would be more. So that's what a type 1 error would be. Let's look at a type 2 error. That's when you fail to reject H0 when it's false. So in this error, it would cause you not to reject the claim that the proportion of contaminated toys was more than 1/100th of a percent when it was actually less. So which one's worse? Would it be worse to believe that the proportion of contaminated toys was less than 1/100th of a percent when it was actually more? Or would it be worse to believe that it was more when it was actually less? And so each one of these has a downside. In the first case, if we believe that the level of contamination is less than 1/100th of a percent and it's more, then we may feel more confident buying these toys and allowing our children to play with them, but they might have a higher incidence of lead, which might cause a physical problem, a health issue for our child. So there's a definite health downside there. But the other situation, if we believe that there's more contamination than there is, then we might say, well, those toys are so contaminated, I would never buy those for my kids. And if that got out, then all kinds of people wouldn't buy these toys for their kids. And so the company would lose profits, right? So there's definitely a financial downside there. So you've got a risk to health in a type 1 error and a profit business problem as a type 2 error. So which one's worse? And I would say that a type 1 error is worse because it could cause harm to human health. You know, causing a problem for the bottom line of a corporation doesn't matter as much as having children get lead poisoning. So in this case, a type 1 error is worse. But in other situations, a type 2 error might be worse. It's just situation to situation. You have to make that determination. You can't always say that type 1 errors are worse or that type 2 errors are worse. It doesn't work that way. It just depends from situation to situation. So no matter what we do, there's always a possibility that we make an error. We can't ever reduce that possibility to 0. We have to live with that. But we can reduce the possibility that we make an error. And that's one of the things we'll be talking about next. We need a definition first. It's the definition of the level of significance. So the level of significance, which we use the letter alpha for, is the maximum allowable probability of making a type 1 error. If we're talking about the probability of making a type 2 error, then we call that beta, which would be the level of significance for making the type 2 error is beta. But in this class, we're going to focus on the alpha. If you took a statistics class that was more advanced, if you have to take more statistics for your major, then you would talk about beta more. But in this class, we're going to focus on alpha. So you may recall we've seen alpha before. We've never used it for anything. But if you look back at some of the distribution tables, you'll see that alpha is at the top of some of those tables, like the t distribution and chi-square distribution. There's alphas on those tables. So if you look at that, you'll see that this is that alpha. Okay. We haven't done anything with it yet. Now we're going to finally figure out what we're going to do with it. Remember that in our hypothesis test, we always begin by assuming that the null hypothesis is true, and then seeing if that leads us to a contradiction. So here's our definition. A p-value. When h0 is true, the p-value is the probability of obtaining a sample statistic with a value at least as extreme as the one obtained from the data. This is basically what we did in the first example that we looked at today, where we talked about those light bulbs, and when we decided the manufacturer's claim was most likely false because it was so unlikely that we would find a sample that had that matching characteristic. That's what we were really doing. We were kind of looking at the p-value. It's the probability of obtaining a sample statistic with a value at least as extreme as the one obtained from the data. There's actually 3 types of hypothesis tests when it comes down to it, and each one is determined by HA, the alternative hypothesis. So the 3 tests are left-tailed tests, right-tailed tests, and two-tailed tests. And HA decides which type of test we're going to use. When it's a left-tailed test, that happens when HA has a less than symbol. A right-tailed test has HA with a greater than symbol, and a two-tailed test has HA with a not equal to sign. And so we have a note. The note is that the smaller the p-value is, the more evidence there is to reject h0. Remember what the p-value is. The p-value is the probability of obtaining a sample statistic with a value at least as extreme as the one obtained from the data. So if that's what the p-value is, if that likelihood is smaller, then there's less evidence to believe the claim and more evidence to reject it. Okay, so when we're using these p-values to figure out these hypothesis tests, we have to interpret them to make our decision. So we have something called the p-value decision rule. The p-value decision rule goes like this. Once you've figured out the desired value of alpha and found the p-value, then you're going to do a comparison test. If p is less than or equal to alpha, you reject h0. If p is greater than alpha, then you fail to reject h0. So the way that this process works is that only h0 can be rejected and only HA can be supported. So it's not that you're looking at a claim like h0 and saying, oh, I'm going to reject that claim, or oh, I'm going to support that claim. You can reject h0, but you can't support h0. Because the opposite choice is you're either going to reject it or you're going to fail to reject it. It's not the same as rejecting this or rejecting that. It doesn't work that way. It's a little bit different. So when you're writing your claims, you have to write them in such a way that you can obtain your desired result. What does that mean? Well, if you want to reject a claim, let's say you think that the claim that a manufacturer is making is false, then you're going to write it to be H naught. If you want to support a claim, then you need to make sure you write it as an alternative hypothesis, HA. Because the results that you have from a hypothesis test is you can either reject H naught or you can support HA. So if I want to be able to reject a claim, it has to be an H naught claim. If I want to be able to support a claim, it has to be an HA claim. Let's take a look at an example. A computer printer manufacturer claims that the average number of pages printed by its XR black ink cartridge is more than 80 pages. Write the null and alternative hypotheses if A, you want to support the claim, B, you want to reject the claim. Okay, so if we want to support the claim, we can only support HAs. So let's look at the claim here. The claim is that the average number of pages is more than 80. So the claim that we will get just by reading is mu greater than 80. So now what is our agenda? What do we want? In part A, we want to be able to support a claim. Well, we can only support a claim if it's an HA. Is this an HA? And the answer is yes. So if you want to support the claim, you state it as HA. That would be exactly this claim, mu greater than 80. And then when HA is mu greater than 80, H naught would be mu less than or equal to 80. So if we want to support the claim, in this case, we'll state it exactly as it is. What if we want to reject the claim? If you want to reject the claim, you have to state it as an H naught. The way that the claim comes out is as an HA. To make it into an H naught, we need to throw an equality in there. So instead of saying mu is greater than 80, we'll say that mu is greater than or equal to 80. That contains the claim that was made in the original statement, along with the or equal to. That makes it into an H naught, which makes it rejectable, because we can only reject the H naught claim. So we'll add in the or equal to, and then that makes the alternative hypothesis mu less than 80. This is not something that I would test you on, being able to shift from one to the other, but understand that sometimes if you believe a claim should be rejected, you need to write it a certain way. If you believe a claim should be accepted, you write it a certain way. So being able to tweak those equations that come out of your statements is important. Okay, so here's a practice problem. A large mortgage firm claims the average number of foreclosure filings per day is at least 210. Write the null and alternative hypotheses if A, you want to support the claim, B, you want to reject the claim. So give this a shot, take a little bit of time, press pause on the video, and when you're all ready, press play. Okay, so let's read this claim and figure out what comes out naturally. The claim is that the average number of pages is at least 210. At least means greater than or equal to, because it's at that level or more. So mu greater than or equal to 210. So this is a natural H naught, but we may have to tweak it to satisfy the question. So the first part is, what do we do if we want to support the claim? Well, if we want to support the claim, this has to be an HA. It's not an HA right now because of the or equal to sign. So to make it into an HA, we'll take the or equal to sign off, which would be mu greater than 210. That's going to be our HA, which would mean the H naught would be mu less than or equal to 210. So that's how we would write these hypotheses if we wanted to support the claim. If we want to reject the claim, then the claim has to be stated as an H naught. Well, the claim naturally came out in an H naught format with the or equal to in it. So we can leave that claim exactly as is, mu greater than or equal to 210 as our H naught, and make the HA mu less than 210. So It doesn't seem like we should be able to do that if we can just pick up the or equal to sign and shift it back and forth. But if you think about it, if I wanted to support the claim, we had to shift that or equal to sign here. If I support that mu is greater than 210, doesn't that also support that mu is greater than or equal to 210? Because to support a claim, one of those things has to be true. At least one of those things has to be true. So if greater than is true, then greater than or equal to is true. So by figuring out one chunk of it, we get both. That's kind of the idea behind it. That's why I wouldn't test you on this particular concept, because it doesn't always make immediate sense. It's one of those very thoughtful concepts that you have to think about for a long time to be able to figure out why it works that way. And I don't think that would be a fair test question. Let's kind of summarize the way a hypothesis test would look. To perform a hypothesis test, you need to know your statistical hypotheses. So you're going to always state your H0 and your HA. Then you're going to determine your alpha, your level of significance. What is the maximum allowable probability of making a type 1 error? Then you need to know what kind of a test you're doing. Is it a left-tailed test, a right-tailed test, or a two-tailed test? You'll find a p-value. Remember that the p-value is the probability of obtaining a sample statistic with a value at least as extreme as the one obtained from the data. Then you'll do a comparison. You'll compare p to alpha to make your decision, where you either reject H0 or you fail to reject H0, and then you'll have to interpret your results. So this has been an intro to the process, but we actually haven't fleshed out the process. That's what section 7.2 is about really getting down to the nuts and bolts of the process. So we'll leave that there, and this is the end of section .1, and have a great day.